Last time I showed you that hierarchy of life, right? And we're gonna climb up that ladder a little bit. We're gonna like hit some of the rungs so we can get up to the place where physiology really lives. But to do that, we need to understand the simpler elements simpler components, to not be confusing, of that. So I had talked about all this, right? I had talked about Aristotle, God love him, and how he believed that complex structures are built from simpler structures. And then there's this guy named Democritus that I don't think I mentioned last time, but some of you probably remember me talking about Democritus, maybe not. And Democritus, another Greek guy that was around the same time, he had a different idea, actually. He had the idea that there were these things called atoms, and they were indivisible, that the universe is not made up of infinitely divisible things, that there are fundamental units. There are fundamental units that cannot be broken up. So that the world is in some measure quantized, right? There are discrete, concrete quanta of something. And this conceptual dichotomy, we'll call it, between Aristotle, who thought that the world was continuous, right? That matter was continuously variable, and Democritus, who thought that there were finite quanta of matter. That is a conceptual conflict in some ways that rages today in so many ways. Now I'm going to go on a little bit of a tangent here so that you can understand maybe like a broader concept here than just anatomy and physiology. But for example, this paradigm can be found everywhere. Like the idea of the analog versus the digital, right? So in the analog would be something like Aristotle, an analog, a concept of an analog sound, like an analog recording. It is like a tape recording, or like a magnetic tape recording, or the vibration of a needle in vinyl, on a vinyl record. That's something where it's not broken up into discrete quanta, that it's continuously variable throughout. Whereas the digital, that information is broken up into discrete ones and zeros. It's digitized, it's quantized, it's broken up into concrete quanta. In another example in science would be the conflict, I guess, the conceptual unresolved, unreconciled conflict between gravity on one hand, which was Einstein and his theory of relativity, and then Schrödinger and this idea of quantum theory. So Schrödinger thought that energy was broken up into discrete packets, and Einstein thought it was quantized. Einstein thought it was continuous. Gravity is this continuous field that exists through space. It happens in politics and social theory when you think about the competing concepts of moral and cultural relativism or humanistic relativism, meaning that the morals or code of ethic within a culture can't be evaluated externally. They have to be evaluated internal to that culture. Whereas there's a moral absolutism. So these would be people who think that there's like an absolute right and wrong that is never variable, and that is at the heart of a lot of the culture wars in our society right now. People who think, any number of things. There's always a right and always a wrong, and there's an absolute versus people who have a relativistic concept of the world. Anyways, all of this was this conceptual difference between Aristotle and Democritus. Democritus' name, as you might be able to guess, he was an advocate, a conceptual advocate for the concept of democracy. The idea that the collective, the whole of the people, the whole of the social compact is made up of individual, indivisible people who each have a say in contributing to the whole. Right? So his concept of the atomic theory, the first atomic theory, was a much more broad philosophy that he had. But the thing is, he lost. He lost, at least at the time, and for about 2,000 years, he lost to Aristotle. Aristotle's concept of the universe, his ontology, held sway for about 2,000 years until a mathematician named Leibniz developed this monad theory, which we won't get into, but a monad is essentially an indivisible component, and that was the beginning of modern quantum theory. And the ideas of Democritus were sort of re-emergent and ascendant. Anyways, first guy to think of atoms was this dude here, Democritus. That was a lot of tangent stuff, but it's all raising the level of your understanding. Okay, I showed you this, right? And we're gonna last time this was just how we investigate the different size scales, and we're gonna walk our way up from atoms up to the person. So, just a little bit of a review over what our modern understanding of an atom is. So an atom is both a particle and a wave. We're not going to get too deep into the philosophy of that because that's a profound concept, the duality of matter. But we're gonna create this sort of materialistic concept of it as physical solid objects, although that's not exactly what reality is. Yeah.
If you don't want to get into this understanding, how is it a wave?
How is matter a wave?
Yes.
Well, it's both. Matter is a wave in that it is an atom is uniquely described symbolically, conceptually by this thing called the Hamiltonian. And a Hamiltonian is basically the wave equation that was first described by a guy named Erwin Schrödinger. The symbol for it is just the capital Phi. That's the Hamiltonian, and it is meant to represent the total energy vector for an elementary particle, an atom, or some quantum isolated item. Sure.
I'm not sure what an energy vector is.
Yeah. Okay. So a vector. Do you know what a vector is? Yeah. Okay. A vector is a quantity that has a scalar unit, just meaning like what's the numeric value of something, the scale, and a direction component to it. There's a scalar component and a directional component. So, for example, a vector could be, I am traveling 35 miles per hour, that's the scalar component, north by northeast, 33 degrees northeast, or whatever. That would be the directional component. So there's a scalar component to a vector and a directional component to a vector. A vector is just like, a vector is basically just an arrow pointing in a certain direction, and the length of the arrow is a measure of the intensity of some scalar value. All right, that's all that a vector is. And you can have vector fields, like when you go on the National Oceanographic and Atmospheric Administration website, the NOAA website, and you look at say you're into sailing, and you go and you look at the map that shows the wind blowing over the Penobscot Bay, and you want to figure out when it's going to be good. There's all these arrows that are all over the water there, all pointing in a certain direction. Some of them are longer and some of them are shorter. The length of them is how strong the wind is, and the direction is the direction the wind's pointing in. Those are vectors. And the entire map would be called a vector field. All right. Anyways, the Hamiltonian is the energy vector for a particle. And it's telling you how much the energy is the scalar quantity. It's like how much energy is embedded in that particle. And the vector is, where's it going? What's its momentum? What's it going to be doing next? That energy is going in what direction? All right? And so the energy is has wave properties to it. All right? Energy has wave properties to it. If you took my chemistry, right? Yeah, and was that the year that I talked about the emission spectra? Yeah, that intense ass shit, right? All of that stuff, those energy levels in the emission spectra, those are energy quanta. It cannot be in the middle of those energy levels. It has to be on one or the other. So it's these quantized energy levels that are a wave. What is a wave? Well, you can imagine a wave as simply being a cycle, right? A wave is something that's oscillating in a cycle, but moving with respect to you. It's got a translational movement. And so when you do that, it looks like a wave, all right? And so particles have wave properties. This is like way beyond what you need to know for anatomy and physiology. But just to this is an important concept, and it's like a foundational, a first principle concept in science, so it's okay. But Erwin Schrödinger came up with quantum theory, and part of quantum theory was developing the math behind the Hamiltonian, which enabled scientists to be able to completely describe and predict the behavior of an elementary particle, or what are called otherwise called quantum isolated entities, right? So these are entities that can be more than one particle. They can be molecules or whatever, as long as a single Hamiltonian, they're quantum isolated. A single Hamiltonian describes the behavior of that molecule or whatever. All right. So, anyways, that is a major tangent. We're not going to worry about the Hamiltonians and wave particles and stuff like that. That was not the best introduction to it either. There's more to it, but it takes more setup to get you to the right point. For now, we're going to go back to, you remember Dalton from then? Dalton was a scientist who basically thought of atoms as being made of billiard balls, little like hard spheres. And so there are two parts. There's the nucleus and then the shell, the electron cloud around it. The nucleus is made up of two types of fundamental particles, protons and neutrons, and then the cloud around it of charge densities made up of what are called electrons. These are the three elementary particles. Probably, who hasn't heard of protons, neutrons, and electrons? Okay, that's everybody. Everybody's got that. Well, protons and neutrons are where the mass, what we perceive of as mass in an atom are. And you're like, well, you said it was a wave. What is mass? I don't know. Mass is simply the ability of an elementary particle to bend space and create, and by bending space, create the perception of gravity, right? And so that's what we see as mass. We see that as mass. So protons and neutrons have mass in the way that we perceive it. Yes, sir?
So is having mass what defines a particle?
No, because there are particles. Oh, shit, this is a much more sophisticated question than you probably realize. There are particles that do not interact with gravity. Okay, there are particles that do not interact with gravity, right? So one of the there's like matter and antimatter, and so apparently the like vast majority of the stuff that is in the universe that's around you right now, that's through everything here, is actually stuff. I don't want to call it matter because it's not matter, but it is stuff that we cannot perceive. That it's there, but we're not able to perceive it. And this is what antimatter is, or dark matter, all that stuff. Yeah. So like it's like fertile ground for sci-fi novels, but that's where physics is right now. So having mass is not what defines a particle, necessarily. But there are things that have mass. Everything we're going to talk about has mass. We're going to talk about protons, neutrons, electrons. We'll talk about photons. Even photons have mass because light has a pressure to it. So, whatever. Good deep thoughts, way beyond what we need to know for here. But keep thinking those thoughts. All right. So the basic idea is that neutrons are neutral, protons have a positive charge, electrons have a negative charge. I'm introducing this because I want you to understand the concept of charge. What you actually need to know here is not all this quantum physics. It's that atoms and molecules can have charge, and the positive charges come from when there is a surplus of protons in that molecule, and a negative charge comes when there is a surplus of electrons in that molecule. That's it. Okay? Does that make sense? Yeah. Basic. All right. Yeah, food is made up of atoms. Okay, and so do I care about this? Maybe. There's this thing called the mass number, and I don't want to get into the weeds of this, frankly. This is.
I remember this from times.
Yeah, good. Yeah, good. So there are things that there are these different numbers that are associated with an atom of a certain element. There's something called the atomic number. That is the number of protons in the nucleus. And it is the number of protons in the nucleus, not anything else, that determines what element something is. All right? So carbon is carbon because it has 6 protons. Period. End of story. That's it. If it doesn't have 6 protons, it's not carbon. If it has 6 protons, it is carbon. So its atomic number is 6. And we organize the elements in order of the number of protons they have, their atomic number. All right? So for a given element, you can have a variable number of neutrons. It, doesn't matter explicitly having, carbon doesn't have to have 6 neutrons. It has to have 6 protons. It can have 6 neutrons, or it can have 7, or it can have 8 neutrons. So I told you that protons and neutrons have mass, and so it's going to give us a mass number. That's the number of protons plus the number of neutrons. The idea that I'm building towards here is the concept of an isotope, because I will talk about isotopes at different points in time, and it's important to understand what an isotope is. An isotope is a variant. Like anybody in the comic books? No one? A few people? Don't be shy. It's okay. Embrace the nerd. Yeah, comic books have variant covers, right? There's the 95% of the covers are cover A, but then 4% are variant B, and 0.5% are C and D, that kind of thing. That's like isotopes. Isotopes of carbon, the vast majority of the carbon out there is called carbon-12. It's called carbon-12. The 12 is its mass number, meaning the number of protons and the number of neutrons. Most carbon is carbon-12. You are mostly made of carbon-12. Some of it is carbon-13. That's carbon that has 6 protons and 7 neutrons. And carbon-13 is interesting because it's NMR visible. I'm not going to go into exactly what that means, but it means you can see it in a special kind of scanner, whereas carbon-12 is invisible. Carbon-14, which has 6 protons and 8 neutrons, that is radioactive. And that's what they use carbon-14 dating to see the age of a bone, because a bone, the carbon-14 in it radioactively decays with time. All right? Okay. So those are isotopes. This mass number, for example, carbon-12, that's, well, I shouldn't say carbon-12. Let's do fluorine. Fluorine-19, which has 9 protons because it's fluorine, and 10 neutrons. Its mass number is 19, but that's not the exact mass of it. Yes, sir.
Study stuff that it like radioactively
Decays.
over time. So does it eventually just stop being radioactive?
That's right. That's what radioactive decay is. So radioactive decay is what happens with carbon-14, for example. It's imagine being able to take, you've got a bunch of like ping pong balls, white ones and orange ones. And the orange ones are protons and the white ones are neutrons. And you can pack them together into a more or less sphere, into a well-packed cluster. 12 of them pack together really well. But if you try to pack 14 in, it's kind of awkward. They don't actually fit very well. And 13 works pretty well. So what happens with time is it pops one of those neutrons out, and it releases some energy, the energy that was gluing that neutron in there. It pops a neutron out, and it goes from carbon-14 to the much more stable carbon-13. The nuclear arrangement is better. That energy, the glue that was holding that neutron in, that's the like high energy, like the gamma radiation or whatever that we perceive as dangerous, right? Because that's very high energy stuff that can cause lots of problems, right? So that's all that radioactive decay is, and it emits some energy, loses a neutron, comes to a more stable arrangement that is presumably not radioactive. All right. So the mass number is not the exact mass of an atom, which are measured in atomic mass units. It's close. They're usually very close. But we're not going to go too deep into this. This isn't a chemistry class. What was the point here? Yeah, isotopes. Yeah, that was the point. So here's chlorine, right? Chlorine has the mass number 17, the atomic number 17, because there are 17 protons in it. That's what makes it chlorine. But there are 2 different isotopes. There is an isotope of chlorine that has 18 neutrons and an isotope that has 20 neutrons. Apparently, those are the 2 stable organizations. I guess one with 19 neutrons isn't even stable at all. But because of that, there is a chlorine that has 35 as a mass number and another that has 37. So there are 2 isotopes of chlorine, chlorine 35 and chlorine 37. When you see those written, they would look like this. Even though you say chlorine first and then the mass number, it's written like that, superscripted first. Isotopes. We will talk about isotopes later. All right, food is made up of, everybody likes food, so maybe that'll help you. Okay. All right. Atoms come together, form molecules, and there are different types of bonds that hold atoms together. A bond is simply the way in which nuclei of atoms are held together by arranging the electrons around them. Okay? When you do chemistry, when you form a chemical bond, you are never changing the nucleus or the identity of the atoms. You're just rearranging the electrons around them. If you're changing inside the nucleus of an atom, that's called a nuclear reaction. We're not ever talking about that here. We're talking about chemical reactions. Chemical reactions are just ways of distributing electrons so that different nuclei of different atoms are held together in a sort of collection that we call a molecule. I know this is very simple, some basic stuff, but we took a step up. We did take a step up the ladder there. Molecules. So there are two different types. There are covalent bonds. Covalent bonds are ones that are covalent. This means that the valence electrons, these are the electrons on the outer shell, the outer electron shell of any of these nuclei, are being shared. So the outer valence electron shell of hydrogen is overlapping and shared with the outer valence electron shell of oxygen. They are covalent. It's a sharing. Whereas ionic bonds are not really sharing. They are one atom gives its electrons away to another. And as it gives its electrons away, so for example, sodium carbonate here, sodium gives an electron, just gives it away to, and carbonate is happy to take it up because it turns out that oxygen is very electronegative. It likes to hold extra electrons. So this is a salt, is what you would call this, a metal salt. The sodium is the cation, and the counter anion is an anion carbonate in this example. Does that make sense? Covalent, ionic, basic stuff. All right, so here's just a depiction of that. This is covalency, right? I should have asked you, but I'm telling you. So here's hydrogen. It has one proton, and there's one electron. It needs two electrons for that shell to be filled. Oxygen has 6 protons, and it has 6 electrons, but it needs 8 in its outer shell for it to be, for that shell to be full. A full valence shell, a shell that has all the electrons in it, is like balanced. Does anyone, like you know, on a tire, that you have to put those little lead weights so that as the tire's spinning, it's like balanced or whatever? Or like a centrifuge, you want to have the test tubes balanced around it. It's like that with these electron shells. It wants balance. And so this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. That turns out to be the right number to balance that outer shell. Okay. Chemistry. Super fast. Okay, we did that. And so something important here about water, though. While we're starting, we just made some water. I wish I could do an experiment. I remember in high school, when I was in high school, my chemistry professor, this guy, Father Kurtz. I went to a Jesuit high school in inner city Detroit. It's so intense. And Father Kurtz had these like gross fingernails because he like cleaned his hands with benzene, super cancerous. He got this contraption that he had made out, this electrolytic thing that had a plug that went in the wall, and it had these electrical wires that went up into this burette that was full of water. It was super dangerous. I don't know how he didn't electrocute himself, but he would electrify the water and hydrolyze the water into its oxygen and hydrogen gas. He'd separate hydrogen and oxygen gas from the water. And then he would take that stuff and remix it and ignite it, and it would blow up, right? It's like the cover of the first Led Zeppelin record, right? Yeah, you remember that, right? I made everyone dance to that. So the Hindenburg was filled with hydrogen, this gas, and somebody unwisely smoked a cigarette, or I don't know what the hell they did, but they blew that shit up and started the ship that sailed for one of the greatest rock and roll albums of all time. Yeah, water is amazing stuff. It's super, whoa. Speaking of explosives, Water is really incredible stuff because we take it so for granted because it's everywhere. It's the liquid of life. It seems so normal and natural to us, but it's like there are no other liquids like it. Water is really bizarre. For a molecule that's this small, to be liquid at room temperature is strange. Everything else that's that size, like carbon dioxide, you have a carbon, which is C6, right? And then 2 oxygens, which are both 8, way heavier than this, than a molecule of water. Carbon dioxide is gas at room temperature. This is propane. That tank over there, 1075 is the code for propane. It also helps it says propane below it. Propane is, I'll draw you a molecule of propane right now. Propane is CH3, CH2, CH3. Way bigger, way heavier than water. That's a gas. Propane is a gas. The fact that water is a liquid at room temperature is bizarre. It's bizarre. And it's all because of the special properties that water has in terms of its dipole, this dipole moment. This is important because a lot of concepts in physiology, it helps to understand what the hell water is doing. When we talk about countercurrent multiplication in the kidneys, for example, it is going to be good to understand and remember the dipole that water has. So dipole, di meaning 2 pole, poles like the North and South Pole. Water is kind of like a little magnet, except it's not a magnet, it's an electric, it's an electric field here. It's a dipole moment. Because water is this bent orientation, it has 2 hydrogens and it has 2 lone pairs. So we draw water often like this, but the reality is it has these 2 big Mickey Mouse ears of lone pair electrons sticking off the back end. It's tetrahedral in shape. If this is in plane, one of these would be sticking out towards you and the other would be going in. All right? So the hydrogen, oxygen, hydrogen is bent. It's a bent arrangement. There's an angle right here. Actually, I think it's like 106 degrees. Because of that, the oxygen, like I already said, the oxygen likes electrons. It pulls the electron that this guy has donated to it even more strongly. Really pulls the electron density this way and this way. And because of that, there is this is a lowercase delta there, and it's used to represent just a small bit of something. There's an extra little bit of negative charge on the ass end of the oxygen. That is reinforced by all of those electron lone pairs over on that end. And it leaves these 2 hydrogens a little electropositive, meaning a little bit positively charged. Not a full formal charge, just a little bit, just a little bit. All of this adds up to be a net dipole along the axis of the water. So water really looks like this. Because of this, yeah.
Net dipole meaning that it's like attracting upwards? Like I don't really
Well, it's not really attracting upwards. It just means that like this end is kind of negative and this end is kind of positive. All right? And because of that, water sort of acts like, did anyone play with Legos when you were a kid? Yeah, Legos. You ever like chew on them and like run them through the vacuum a couple times and like play with them in the sandbox so you got nice and sandy? And so the Legos stopped like sticking together super well. You could get them to stick together, but they weren't like, brand new Legos that are super, super tight. That's kind of like water, all right? Let's see, what pictures do I have here? Okay, not quite yet that. What water looks like in a cup of water is we are able to form hydrogen bonds. the positive, the little delta positive on this water molecule, this hydrogen, is able to, it gets attracted to the negative on this one. So water molecules are a little sticky to one another, all right? But it's transient, meaning it's like short-lived. It doesn't last forever, right? And it's this huge network, right? It's all over the place. This huge network of hydrogen bonds in a glass of water. They're constantly forming and then breaking apart because they're like crummy Legos. Yeah.
Is that why surface pressure?
Surface tension. That's right. It's exactly why water has high surface tension. It's because all of this hydrogen bonding. That's not happening in propane. It's not happening in CO2. Yes, sir?
So if something floats on the water, it's just because it doesn't break the hydrogen bonds?
That's right. That's right. Exactly. It's also, so surface tension is also what gives us capillary action, which allows water to flow up through a capillary. It's why water flows up into trees against gravity, for example, and there's all kinds of capillary action in the capillaries of your body, for example. Yeah, surface tension of water. So it's important to understand why water is the fluid of life, because a lot of physiological processes that we'll talk about will require an appreciation of that fact. Okay. By the way, I should have introduced this at the beginning of the class. I'm just going to say it because it's 2019. I prefer he, her, his, and if I use pronouns for any of you that don't match what you prefer, please correct me or tell me what you like. All right, let's move on. So next, onto the concept of a solute. We're like whipping through a semester of chemistry in one fell swoop here. A solute is, this property of water is, it means it's a polar molecule. It's polar. It has these poles, right? A negative and a positive pole. There are nonpolar molecules. When we talk about fats are nonpolar molecules, and there are nonpolar forces as well that guide the way things happen in our cells. For example, the formation of the lipid layer around the outside of a cell is because of the hydrophobic or nonpolar forces that exist in fats. But we'll look at that in a bit. Anyways, a property of polar molecules and polar liquids is that they can dissolve ionic compounds. Molecules where it was not electron sharing, it was electron donating. All right. Is this good, or am I going over? Is this boring? Am I going over stuff you've already heard? Keep going with it. Go faster. Go slower. You got to tell me.
Good speed, faster.
Okay. So good pace, maybe a little faster. All right. Anyways, so here is everybody's favorite table condiment, table salt, sodium chloride. All right. It's an ionic compound. It exists in a gorgeous crystalline lattice, right? So sodium chloride looks like this. Right? And then that goes back into a cube, right? I'm imagining you guys have seen crystal lattices of, a salt crystal, I'm sure. If you ever looked at a salt crystal under a lens or grown something big. Anyways, this salt crystal goes into a cup of water. Let's make this a cup of water. And what happens is the water, all these partial charges, all these partial negative charges, they start eating away at the edges of the crystal. They are able to overcome the crystal lattice forces. So this is a lattice, like in your garden, you have the lattice and the ivy grows up it. The crystalline lattice is held together by the attraction of a positive sodium to a negative chlorine, and so on and so forth in all three directions around it. But The negative end of water says, hello, sodium. And they pull sodium off and stick their negative butts right around the positive charge of the sodium and kind of isolate and balance off that charge. Whereas the other end, the positive front end of the water molecule says, howdy doody chloride, and surrounds the negative charge with all of its little partial positive charges. So now this molecule of sodium chloride is a sodium ion and a chloride ion that are separated from one another and in dissolution. This is the magic of taking salt and swirling it and watching the crystals disappear into water. Still a pretty magical thing that happens. Okay. So positive charges are called cations, negative ones are called anions. We will revisit this later when I talk about osmosis and establishing charge dynamics across a membrane. It gets more intense, but that's how that works. All right. Yep. So we talked about this. This is also why, this is interesting, this is why ice floats. Give me another substance where the solid phase is less dense than the liquid phase. There isn't one. Think of one. Try. Water is really dense. And it's because of these hydrogen bonding networks that exist in liquid water. Like, for example, butter. When you melt butter, the chunk of butter is at the bottom if it's like doesn't have a lot of water content in it. Or like, for example, if you get olive oil and put it in the freezer and then let it melt, the solid stuff is at the bottom and the liquid is at the top. Not with water. And here you can see some capillary action. Convenient arrow right next to it. All right. So, okay, and getting near the end of our chemistry lesson here. Acids and bases. It's important to understand acids and bases. Water can dissociate into H plus and OH minus. Sometimes, so if we go back here, we see this water molecule is hydrogen bonded to this water molecule. Sometimes this water molecule says, gimme, 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 so hard that this hydrogen kind of goes over here like this. And this thing becomes H plus, and this is OH minus. In fact, it's not H plus, it would be H3O plus is what that is, the hydronium ion. Okay? So we have a little bit of a dissociation. You see it written as this formula right there. That's not actually what happens. It's actually this. That's the actual reaction that's happening. But they do it shorthand because the overall effect is to have one water molecule split into hydroxide and a hydrogen ion. All right. In pure water, in totally distilled water, free of any other solutes, the concentration of this is going to be 1 times 10 to the negative 7th. All right. Moles per liter. Does everybody remember what a mole is? Who does not know what a mole is? I'm not talking about the blind little rodents. Yeah. Everybody's good? So a mole is just a number, very large number, 6.022 times 10 to the 23rd. So in 6.022 times 10 to the 23rd molecules in a liter, 1 times 10 to the negative 7th of that ratio is going to be one of these things. So pH is defined as the negative log of the hydrogen ion concentration. I told you the hydrogen ion concentration in distilled water is 10 to the negative 7th. Because of the properties of log, that means that the pH of a distilled water equals 7. Okay? Does that make sense? The negative here cancels out the negative there, and the log of a number that's held to an exponent is just that, of 10 held to an exponent is just that exponent. All right? That's some math. Anyways, pH, what that's telling you is that the hydrogen ion concentration is 10 to the negative 7th. That concentration is 10 to the negative 7th. As the number goes up, 1 times 10 to the negative 3rd, for example, what would the pH be of a hydrogen ion concentration of 10 to the negative 3rd? Yeah. 3. That's it. 3. Which of these two is a bigger number? So 1 times 10 to the negative 7th, just to remind you, is 1 over 10 to the 7th. And 1 times 10 to the negative 3rd is 1 over 10 to the 3rd. Which of these two numbers is bigger? Yeah.
1 over 10 to the 3rd.
That's a bigger number, right? Which means that it's a higher hydrogen ion concentration, right? In this instance, 1 molecule out of every 10 to the 7th is a hydrogen ion. In this instant, 1 out of every 10 to the 3rd, 1 out of every 1,000 molecules. This is 1 out of every million, okay? And so a pH of 3, where the pH is going down, is something that's more acidic, meaning there are more hydrogen ions in solution. Is that making sense? So for example, maybe you dump some HCl, hydrochloric acid, in there. This is an ionic compound. It dissociates into H plus and Cl minus. Are we at the bewitching hour? 1 minute. Let me finish this thought. We dump this stuff in. Chloride isn't going to affect how much hydroxide is there, but we're adding hydrogen ion to the solution. So that pH is going to go down. Acids, so decreasing pH means that we are increasing the amount of hydrogen ion that's in the solution. And conversely, an increasing pH means we're decreasing hydrogen ion concentration and increasing the amount of hydroxide that's in that water solution. Acids and bases are the most complicated idea that I'm giving you today. But we will need to understand acids and bases because they're super important to life. That was a lot. That was a lot for one day. Any questions? I put the lecture up on the classroom, and I'll do the same with this one.